When you look up at a massive high voltage transmission tower, it's easy to just see, well, static cables, right? Just hanging quietly in the sky. But honestly, that couldn't be further from the truth. The high voltage power grid is absolutely not a static set of wires. It's this dynamic, living system that is constantly locked in a high stakes battle against the laws of physics. So, welcome to The Explainer. Today, we're going to uncover the invisible warfare happening right above our heads. Here is our roadmap for today. We're going to look at the invisible threats of the grid, the corona discharge glow, the counterintuitive Ferranti effect, how we actually mitigate these hazards, and we'll wrap up with a high-voltage head-to-head. Let's decode these mysteries. All right, starting with Section 1, Invisible Threats of the Grid, the sensory signs of a stressed system. I want you to think about a time you might have been walking near a really massive overhead power line. Have you ever heard it crackling? It's a bizarre, almost frying sound coming from up there. It sounds kind of like bacon sizzling, but it's happening hundreds of feet in the air. What you're actually hearing in that moment is the grid under intense physical stress. And that stress, it isn't just auditory, it's a full sensory experience. If you know exactly what to look for, especially at night, you might spot this faint, luminous, bluish-purple glow wrapping right around the conductors. Along with that hissing or crackling noise, you might even catch a very distinct metallic smell in the air. That's ozone. These are the vivid, real-world symptoms of a grid pushed to its absolute limits. But what is actually happening up in those wires to cause all of this? That brings us to Section 2, the corona discharge glow, or what happens when the air breaks down. Okay, to understand that weird blue glow and the hissing sound, we have to look at the physics of the air itself. It all comes down to dielectric breakdown. This is basically a localized electrical breakdown, or ionization, of the air surrounding a high-voltage conductor. See, under normal conditions, the air around us is an excellent insulator. It keeps the electricity safely inside the wire where it belongs. But when you raise the alternating voltage on a transmission line, the electric field, the potential gradient right at the surface of that conductor, shoots way up. If that electric field gets intense enough, it can literally overwhelm the insulating properties of the air. It ionizes the air molecules, and suddenly the air itself becomes conductive. And this breakdown doesn't just happen at random. It happens at a very specific mathematical threshold, 30 kilovolts per centimeter. When the electric field exceeds this peak at standard temperature and pressure, the air just gives way. The electricity literally leaks out into the surrounding atmosphere, and that is what creates that faint bluish-purple aura we call corona discharge. So it looks kind of cool, right? But it's definitely not just a pretty light show. The operational impacts here are severe. First off, there is a direct, real power loss. The grid is literally bleeding usable energy into the sky. Operators call this corona loss. Second, all that ionization creates electromagnetic interference. It can completely disrupt local radio and television signals. And finally, remember that metallic smell? That's the generation of ozone gas. Now, ozone is great high up in the atmosphere for sure, but down at the conductor level, it causes terrible accelerated corrosion on the system hardware. So yeah, it's a costly, damaging electrical leak. Moving on to Section 3, the Ferranti Effect, the danger of an empty line. This is a totally different, counterintuitive threat to the grid. This one is a complete mindbender. Get this. The voltage at the receiving end becomes higher than the voltage at the sending end. Imagine turning on your garden hose and the water pressure coming out of the nozzle is somehow way stronger than the pressure back at the spigot. That is essentially the Ferranti effect. When a medium or long transmission line is basically empty, meaning it's operating under no load or really lightly loaded conditions, sending electricity down the wire actually makes the voltage increase at the destination. How on earth is that possible? Well, let's walk through the chain reaction. Step 1. Every transmission line has this natural distributed capacitance between its conductors and the ground below it. When the line has no real power load at the end, this capacitance naturally draws what we call a charging current. Step 2. Because this current is capacitive, it leads the voltage by exactly 90 degrees. Step 3. As this leading current flows down the wire, it passes through the line's distributed inductance. And Step 4. This creates a voltage drop that is perfectly in phase with the sending end voltage. It's exactly like pushing a kid on a swing at the absolute perfect millisecond. The energy cumulatively adds up along the length of the line, driving the voltage higher and higher the further it travels. Now, this isn't just some quirky physics trick you do in a lab. It is a massive problem for power operators. This over-delivery of voltage causes severe insulation stress on downstream transformers and relays. If you suddenly hit a transformer with a significantly higher voltage than it's physically built to receive, you can severely damage crucial grid infrastructure. It can even trip the distance protection relays, which could potentially cause cascading power outages. An empty line is literally a dangerous line.
Okay, Section 4, Mitigating High Voltage Hazards. How we actually engineer the solution. We've seen physics trying to break the grid apart, so let's look at how we fight back.
Let's tackle that first threat. Fighting corona discharge basically comes down to manipulating geometry. Since the discharge is caused by a highly concentrated surface electric field gradient, engineers just outsmart it by increasing the effective diameter of the line, right? A thicker line spreads that electric field out over a much larger surface area, which drops the gradient well below that critical 30 kilovolts per centimeter threshold. And they achieve this cleverly. They use bundled conductors, where several smaller wires are grouped together so they act like one giant wire, or they just use hollow conductors. Problem solved. Now, fighting the Ferranti effect? We don't use geometry for that. We fight it dynamically. System operators use reactive power compensation to tame that runaway excess voltage. Typically, they'll install these massive shunt reactors right at the receiving end of the line to literally absorb the excess leading reactive power. Plus, they use FACS controllers, flexible AC transmission systems, like SVCs and STATCOMs. These are highly effective automated systems. They dynamically manage reactive power and stabilize the voltage profile the very moment those transient load changes happen. They basically keep the swing from going too high. All right, Section 5, the high voltage head-to-head. Corona versus Ferranti. Let's put these two side by side to really lock this in. Let's look at the core differences. By nature, corona is a dielectric breakdown of the air, while Ferranti is a steady-state overvoltage condition. The cause? Corona is driven by a high surface electric field gradient, but Ferranti is driven by capacitive charging currents. Now, consider the conditions. This is interesting. Corona happens regardless of load, but it's heavily worsened by foul weather, like rain and high humidity. Ferranti, on the other hand, is triggered by a lack of power demand. It happens mostly under no load or light load conditions. Corona doesn't really alter the overall macroscopic voltage profile, but it does cause real power loss, noise, and that corrosive ozone. Ferranti does alter to voltage, massively stressing downstream insulation because the receiving end voltage becomes greater than the sending end. Basically, one bleeds power, the other forcefully pushes too much. It's honestly an incredible balancing act, keeping our modern world cowered. Every single time you flip a switch in your home, there is a literal symphony of engineering actively fighting off ionization and capacitive voltage spikes just to keep the lights on and the grid stable. Which brings us to a really critical thought to leave you with. As global power demands continue to surge, and as we push our transmission lines to carry even higher loads over longer and longer distances, what new, unseen phenomena will our engineers have to outsmart next? It's a fascinating question, and one that ensures the world of power engineering will absolutely never be a static field. Thanks so much for exploring the grid with us on this explainer.